one is going to be associated with questions 1 and 2 for us, all right? So resting pulse rate is an important measure of the fitness of a person's cardiovascular system, with a lower rate indicative of greater fitness. The mean pulse rate for all adult males is approximately 72 beats per minute. A random sample of 25 male students currently enrolled in the agriculture school at a major university was selected, and the mean resting pulse rate was found to be 80 beats per minute, with a standard deviation of 20. The experimenter wishes to test if the students are less fit on average than the general population. So, if we're looking at this, okay, so first, for the null hypothesis, I'm seeing two different symbols here. I'm saying half of them use mu, half of them use x bar. Which one is appropriate for your hypotheses? Which one have we always used when writing hypotheses? We've always used mu, right? Your hypotheses should always be geared towards a population, not your specific sample, all right? So right off the bat, I can rule out any of these that use, any of these that use the x bar, okay? Because you're looking for something using mu, not x bar. Other thing, notice you also see some of them using 72, some of them using 80. Which number is appropriate here? 72, because that's what we're saying is true for the population, right? We don't want our sample represented in our hypotheses. The hypothesis is about the population. So I would also rule this one out because it's using the wrong number, okay? Final thing about the null, shouldn't the null always be equal to? So the last two we have, we're good to go, right? So now the focus needs to shift towards the alternative. Obviously, the alternative is going to be the reason that we can pick one of these over the other. So the alternative is where you have to pay attention to the direction, all right? Now here you have to be really careful. So we're testing to see if these individuals are less fit. Okay, we think our sample might show that the individuals in the sample are less fit. Now, be careful the way that you do this, though, because what would it mean to be less fit in this case? Does less fit mean less than in this case? It means greater than, because didn't they specify up here a lower rate is indicative of greater fitness? So if we think they're less fit, aren't we worried that they might have a higher rate? Right? So just be careful when you're looking at the direction that you're aiming that alternative. Okay? This one is a little bit tricky because it feels kind of backwards from what you would expect. Which of the following describes a type 2 error? Now, for this, I would honestly, I would go with my strategy I kind of talked about last chapter. I would have in my head what I'm looking for before I read any of the answer choices here, okay? Because again, they're all going to sound very similar, and they're very good at making traps for you, okay? So, type 2 error. So type 2 is where you don't get the evidence that you should, but you really should have, right? You don't get evidence, but you should have actually gotten it. So us not getting our evidence, okay? Us not giving evidence is saying we didn't get evidence that they're less fit, but the people actually are. That's the error in it, right? We don't conclude the less fit, but they actually were. Which one of these phrasings best matches what I just said? Not determining the people are less fit, but they actually were. Which one matches? B, not concluding less fit than the general population, when in fact they are. Perfect. All right, are we okay with that? Yeah. Again, I know the type 2 versus type 1 does just take a lot of practice. You've noticed I've done it every single day because I'm hoping the more you do it, just the more comfortable you are with those strategies. Here, a significance test was performed to test the null hypotheses that mu equals 2 versus the alternative mu does not equal 2. A sample size of 28 produced a test statistic of this. Assuming all conditions for inference were met, which of the following intervals contains the p-value for this test? All right, now remember, test statistics like this, Okay, aren't they basically glorified z-scores in a sense? Right? Not exactly, because this is a t, not a z, but isn't that really what we're talking about? We're basically talking about a z-score, right? Essentially. They're talking about the conditions being met. What's the main condition we care about? What's kind of the big one that we always have to check? Normal, okay? So yeah, we always check random independence, but isn't normal where we spend most of our conversation time when we're talking about conditions? So here we have kind of a z-score. We know that this is normal because they told us that the conditions are met, and they're asking for the p-value. Isn't a p-value basically a probability? Right? So basically we have a z-score for something normal. We want a probability. What do we do? All right, so normal CDF is where our heads are at, right? Now, technically, though, oh darn it. Sorry, it's going to take a minute for my calculator to pop up. Technically, is this going to be a normal CDF, though? No, doesn't normal CDF require Z's? What's that next best thing when we kind of have a Z, but we don't because it's a T? TCDF, okay? And I'm sorry, give me 1 second. My computer's really slow. So this is going to be that TCDF command, okay? Oh, come on. One thing that's going to ask us for is the degree of freedom. What degree of freedom do we need in this case? 27, right? One less than our sample size, right? I'm sorry. That computer takes forever. Come on. I'm so bored. Oh, here it is. Okay. Oh, nope, still thinking. All right. Ugh. So, when it's a Z, we could do this with normal CDF, but because it's a T, we're going to be talking about TCDF, okay? Basically the same command. It operates the same way. Look at the way that it's set up. Lower bound, upper bound, all that stuff. What was the value for this? 2.051. So, 2.051, we're going to be heading upward, right? Then we said what, 27 degrees of freedom, right? Now, I will tell you though, that's not actually our final answer, okay? What's one thing we also have to notice about the alternative? The alternative is not equal to. Isn't this just greater than? Right? How do we handle when it's not equal to? When it's a two-sided test, what do we also have to do? Multiply by 2. And again, we're only doing this because the alternative is the not equal to, okay? If it were simply greater than, that first one would have been the answer, okay? But because it's not equal to, because it's a two-tailed test, we have to multiply that probability by 2, okay? And then it's slightly over 0.05, so that would be E, because it's ever so slightly bigger than 0.05. Also, again, just a side note for you, on my list of skills that are important to have, another one to note specifically is I can calculate a p-value from a given test statistic. Well, does that sound something similar to number 3? I can calculate a p-value when I'm given a test statistic. Do you think something like that might pop up? Probably. I'd say so. All right. Some people say that more babies are born in September than in any other month. To test this claim, you take a similar sample of 150 students at your school, find that 21 of them were born in September. You're interested in whether the proportion born in September is higher than 1/12, what you would expect if there's no difference from any other month. Your null hypothesis is that the proportion should be 1/12. Your p-value for your test is 0.0056. Which of the following statements best describes the p-value? All right, so p-value. When we're interpreting p-value, what we're talking about is assuming the null is true. So given that the null is true, It's the probability of getting a sample at least as rare as ours. Okay. So again, this is an interpreting one. So I'm looking at it and I'm not even looking at my answer choices yet, right? I'm getting in my head first. What am I looking for? Then I'm going to read my answers. Okay. So given that the null is true, so given that the true proportion should be 1/12, okay, there is a 0.0056 probability of getting a sample proportion at least as rare as ours. Which one sounds like that? Hmm? 0.0056 is the probability of getting a sample with a proportion of birthdays this far or farther above. Isn't that at least as rare as? Kind of a synonymous way of saying that. If the true proportion is this, if the null is true. Did this hit both components I always talk about in interpreting p-value? Right? The probability that we're getting something at least as rare as ours, given that the null is true. Okay? So I would say D is the best one. Again, also note on this list, if you have this out like I asked, on this list, thank you, it talks about I can interpret a p-value. Do you think that might be a good one to know? Interpreting a p-value? I'd say so. Yeah, probably. All right. Number 5, looking online, you find the salaries of all 25 players of the Chicago Cubs as of opening day of the 2005 baseball season. The club total was $87 million, eighth in the major leagues. Which inference procedure would you use to estimate the average salary of the club's players? Or, sorry, Cubs, not clubs. I will tell you, this is actually kind of going to feel like a trick question to you. Because if you look at this, salaries of all 25 players. So did they do random selection here? No, they took all the data. Would you even have to do inferencing if you have literally all the data to find the average? No. So for two reasons. One, this isn't a random selection, so you wouldn't be able to do inference anyway. Second, inference is pointless because you have all of the data. Why would you need to make a confidence interval if you can literally just find the true mean because you have all the data already? Does that make sense? Yeah. So in this one, unfortunately, kind of feels like a trick question, but you actually would not do it in this case. Okay? If you have all the data, it'd be pointless. You know what the true mean is. All right, so this one we're going to use for 6 and 7. A medical experiment compared the herb, echinacea with a placebo for preventing colds. The study used 50 different response variables usually associated with colds, such as low-grade fever, congestion, frequency of coughing, etc. The subjects were 40 women between 25 and 40 years of age. At the end of the study, that group displayed significantly better responses at the 0.05 level for 3 of the 50 response variables studied. Which of the following is an appropriate conclusion to draw for this study? So here, wasn't this one of the things I cautioned you on? Why would we be cautious from the get-go looking at this study? Does anybody remember one of the things I said be careful for when you're looking at statistical data, something you shouldn't do? What did they do that we shouldn't? No, that's not what I'm worried about. Yeah. Yeah, they ran this test 50 times. Do you want to look at multiple tests and be like, hey, look, a small handful of them are significant, therefore we found something important? Is that wise to do? No, because again, isn't it very possible that these 3 that came up as significant, only 3 out of 50 came up significant? Couldn't those 3 honestly just be type 1 errors? Right? Isn't that very possible? That's why you don't want to do multiple tests and rely on hoping that maybe a few of them turn up significant, because those couple that turn up significant could honestly just be type 1 errors. Okay? So here, I think E would be the best answer for that one. One response variable was volume of nasal nasal secretions. If you have a cold, you blow your nose a lot. Take the average volume of nasal secretions in people without a cold to be mu equals 1. An increase to mu equals 3 indicates a cold. Which of the following describes the significance level of a test of it equaling 1 versus it being greater than 1? This one, again, is honestly kind of a weird question, but I like talking about it just to get you thinking in a different way, okay? So they're talking about significance level, okay? Now, when it comes to significance level, we said actually that is exactly equal to another concept we've talked about this chapter, right? Does anybody happen to remember the significance level equals something else we've talked about a lot throughout this chapter? What does it equal? The probability of a type 1 error, okay? So that significance level is actually the exact same thing as a type 1 error, okay? Well, type 1 error, let's consider that then. So isn't a type 1 error when you reject the null, but you really shouldn't have, right? Isn't that type 1? We reject the null, so we found evidence for this, okay, but we shouldn't have, all right? Which one of these talks about rejecting the null when we shouldn't have actually rejected it? The probability test rejects this when it is actually true. Boom. Again, don't worry, that one, there's nothing like that on the test, okay? That's kind of a weird one, but again, I just think it's interesting to talk about to get you thinking in a different way, all right? A significance test was performed to test the null hypothesis that versus the alternative that is greater than 0.5. The test statistic was z equals 1.4. Which of the following is the closest to the p-value? Well, actually, funny enough, didn't we honestly just kind of do this? Yeah. I'm giving you a test statistic, which again, isn't this basically a glorified z-score? If we're running a test, don't we know we're talking about something normal? So we have a z-score for something normal. We want a probability. What command do we get to use for that? Normal CDF. And this time, do we legitimately get to use normal CDF this time? Yes, because it's a z. What did we use the other time when this was a t, not a z? TCDF, okay? So those two commands, again, they go hand in hand. They operate the same way. You just use normal CDF for Z's, TCDF for T's, okay? So, normal CDF, was it 1.4 something? Oh, it's actually 1.4, perfect. Now last time I needed to multiply it by 2, right? Do I need to do that this time? No, because this time the alternative was in a single direction. All right, so here, this is actually the answer. Remember, you only double it if you have a two-sided test because the alternative is not equal to. All right, are we all okay with that difference? Yeah, excellent. And that would give us, go back, that would give us A. A test of mu equals 60 versus mu does not equal 60 produces a sample mean of 58 and a p-value of 0.04. At a 5% level, which of the following is an appropriate conclusion? So whenever we're trying to draw a conclusion, okay, don't we always focus on the p-value? Isn't that really the critical component to making a choice, to making a conclusion, a decision about this test? So at the 5% level, notice our p-value is less than that 5% level, right? So because that 0.04 is less than the significance level, what decision do we come to? If we were writing out our conclusion, what would we call that? Rejecting. Okay, so we are rejecting that mu is 60, and aren't we concluding that it's not 60 then? We're rejecting this for this. Is everybody with me on that? So which of the answer choices talks about we do have enough evidence to reject this in order to conclude that? B? Oh, E, sorry. There is sufficient evidence. Yeah, love it. We want to test that the null is 1.5 versus it not being 1.5 at a 5% level. And they give us the 95% confidence interval. Okay, based on this finding, we can. Now, remember I said I actually got really excited when we got to this day because I love the relationship between hypothesis testing and confidence intervals. So I want you to note this 1.5. Okay, this 1.5. What do you note about it? It's in it. Okay, the 1.5 is in our interval. Would we reject a value that we believe to be possible? Would that make sense? No. So if we're not going to reject it, what do we do? Fail to reject it. Voila. Wow, you guys are cruising. Because how many more do we have? Okay. All right, which of the following increases the power of a significance test? All right, so power. We've talked a couple ways to manipulate power and manipulate the probability of type 1 and type 2 errors. Now remember, well, first of all, I guess, what are the two ways we commonly try to manipulate them? Perfect. Now, also remember, those two things always go hand in hand, right? Like if we're manipulating power, sample size and the significance level are going to act the same way, right? So for any component we're talking about, those two things are going to either both go up or both go down to manipulate it, all right? To increase power. So then what the question really becomes is, are we looking for more data and a bigger sample size, or less data, smaller sample size, in order to make a more powerful test? What? Wouldn't it make sense if we want a more powerful test, we want the test to be able to do its job the best it can? Wouldn't it make sense having more data helps with that? Right? The more data we have, the better the test will be at doing its job, right? So to increase the power of the test, we want the sample size up and the significance level up. All right, both things go up to make a more powerful test. So which one of these matches what? D. By the way, I think also on my sheet, I think it talks about being able to manipulate these things. That might be a good one to study too. Um, A researcher wishes to determine if people are able to complete a certain pencil and paper maze more quickly while listening to classical music. Suppose previous research has established that the mean time needed for people to complete a certain maze without music is 40 seconds. The researcher therefore decides to test these hypotheses, where mu is time in seconds needed to complete the maze. To do so, the researcher has 10,000 people complete the maze with classical music playing. The mean time for these people was 39.92 seconds, and the p-value is 0.0002. Which of the statements below describes the appropriate conclusion to draw from this study? All right. So with this p-value, what would our conclusion be? Is this a significant difference or not a significant difference? AKA, would we reject or fail to reject the null? We would reject it, right? So we are saying that the data is statistically significant, okay? Now, let me draw your attention to something though, okay? While mathematically this is statistically significant, okay? Let's really take a look at what they did. So we're talking about 40 seconds to complete a maze versus 39.92 seconds to complete the maze. So while maybe that is statistically significant, do we really care? Not really. We're talking about 0.08 of a second. Okay, so, and the reason for that is notice how many people they used. Wasn't that another caution I talked about? That if you have an insanely large sample size, you can even make the smallest difference actually look significant, even if practically it doesn't really matter, right? Do we care about 0.08 of a second? Probably not. So I think the best answer, maybe you could help me find the best answer here. Which one kind of talks about or has the same kind of conversation or flow as what we just talked about. Although the researcher obtained a significant result, it appears to have little practical significance. Perfect. All right, the infamous psychologist, Dr. Weisgrip, claims that his secret sleep tapes cause people to become better at basic algebra. All you have to do, the doctor explains, is listen to my tapes while you sleep at night. You'll be better at algebra in 2 months. A math teacher at a local high school has expressed interest but demands evidence. 5 people are randomly selected from the students at school. They take an algebra skills test, listen to Dr. Weisgrip's tape for 2 months while they sleep, and then take a second test. Which of the following conditions must be met in order to use a T procedure on these paired data? Okay, so they do tell us that this is paired data. All right. So we're talking about checking for normality. Okay, so if you look at every one of these multiple choice, each one of them references normality, right? Now, do we really care about the pretest? Is that the focus of our study? Do we care about the post-test? No, what do we really care about? Only the difference, right? I only ever made you perform data on the difference between them, right? Whether that means graphing to check for normality, running the test, anything, we really have ever only cared about the difference in the data. So here, that's the only thing we would really have to check for normality, okay? You don't have to check all 3. You only check the differences. Bags of a certain brand of tortilla chip claim they have a net weight of 14 ounces. Net weights actually vary slightly from bag to bag and are normally distributed with mean mu. A representative of a consumer advocacy group wishes to see if there's any evidence that the mean net weight is less than advertised and intends to test those hypotheses. A type 1 error in this would mean, all right, type 1 error. So again, before we read anything, all right, tell me just in general terms, what is type 1 error? Not even context, just general. Reject the null when you shouldn't. Beautiful. So we don't conclude this, but we should have. No, wait. I'm sorry. Yes. Sorry. You reject when you shouldn't have. We do conclude this, but this isn't true, right? We conclude that it's less than 14 when it's really not. All right. Which one of those matches what I just said? We do conclude this when we shouldn't have. Which one? A. Concluding the bags are underfilled when they actually aren't. Yeah. Beautiful. A medical researcher is working on a new treatment for a certain type of cancer. After diagnosis, the average survival time for standard patient or on the standard treatment is 2 years. In an early trial, she tries a new treatment on 5 subjects, found that they have an average survival time of 4 years after diagnosis. Although the survival time has doubled, the results of a t-test for mean survival time are not statistically significant, even at the 0.1 level. Which of the following is the best course of action for the researcher? All right, so her data does imply that there is statistical significance here, but the test says otherwise. All right, now this is kind of a double-edged sword, if you will, because I've cautioned you about on an earlier one to not have a crazy big sample size, right? When they had 10,000 people, they made anything look significant. No matter how small the result was, it was going to be significant. Well, the reverse is true also. Here, she only used 5 people. Wouldn't it maybe be more powerful of a test if she had a couple more? Because what is usually the goal? Not 5, but 30, right? Isn't 30 that benchmark for normality? So if she could get closer to that, wouldn't it be a lot more possible that she could have a test come back as significant, right? In this case, I think there's just few 2 people, right? There isn't enough data to show significance if you're only looking at 5 people. You just need more data in that sense. But don't go crazy and do like 10,000 because then your result will automatically be significant even if it doesn't matter. Um, you're testing the hypothesis that a new method for freezing green beans preserves more vitamin C in beans than the conventional freezing method. Beans frozen by the conventional methods are known to have a mean vitamin C level 12 milligrams per serving, so you're testing these where mu is the mean number of vitamin C in the beans frozen. You calculate that the power of the test against the alternative is 0.75. Which of the following is the best interpretation of this value? All right. So interpreting power this time, which again, I will tell you is on your test. All right. You will have to be able to interpret power for me. So again, let's just think about taking a step back. In general, what have I said the power is? Not even worrying about the context right now, just the basics. What is power? Bingo. The probability that the test will properly reject the null. So given that the null actually is false, the probability that your test will reject it. Is everybody with me on that? All right. Now, in this case, they do give us a little bit more background. They're saying if this were actually the true null, there's a 75% chance it's going to do its job. So here there's a little bit more information than we're used to getting. But again, the basics behind it is if the null actually is false, then in this case, there's a 75% chance that this test will reject it. Okay, that's what this number means right here. When they actually gave you a numerical value for it, they're saying if the null is false, if it is supposed to be this, 75% chance that your test will make that right conclusion and will reject that null. Which one sounds like what I just said? The probability of concluding the true mean. Well, no, because we want to conclude this. It's a probability it properly rejects the null. Wouldn't that be? No, I think it'd be E. It's a probability that it concludes this, and in this case, they gave us a specific mean that could actually be. The one on the test is actually easier than this, I will tell you that. It doesn't give you all that extra stuff to juggle. Wow, look at you guys. I'm proud. We actually got through all of that. Um, just checking. I did give you the review packet on Friday, right? Yeah, okay. So you do have that. Remember that, and what else are going to be due on Wednesday for me? What else will you collecting Wednesday? Yeah, both of these will be collected on Wednesday, okay? Both packets are up at Schoology, okay, so you can be looking as you go. Yeah, just make sure that you're working on both of those for me. Yeah, yeah. Was that fast enough? Yeah. Yes.
need to pay me. I just need this stuff.
I just want to do this. But here we still have 7 more minutes. Wow, we actually flew today. Are we feeling pretty good about 9?
I like that you made like a little cheat sheet thing. Like
I was so proud of that.
like you should do that every single day. Oh, because then I can highlight what I don't know.
Ooh, there you go.
Isn't the sheet neon green already?
Yeah, I
If you
use
highlight it,
I
it's
use orange, not yellow. I'll use pink next time.
See, I don't think 10 really. 10 won't need a cheat sheet though. Because 10 is honestly, so like, 8 and 9 feel like one sample. 10 is literally the same thing, but two samples.
Two sample, I called it.
Two samples. Which actually leads to more interesting conversations because it makes more sense. Like rather than testing like a number, you take two different samples and compare them to each other. So that's really what chapter 10 is about. So all the skills are kind of the same. So like, yeah, we'll talk about errors still, but you already know. So, and actually the math gets easier. I learn all the things.
I heard my mom asked you if I used my task.
Yes.
I was like, because I saw, because she writes notes, because she's at work like
sure that we're signing up for that. Because after that deadline, it's much more challenging, and you have to pay an extra fee to get registered. So make sure you're doing that this week, please.
All right, bye, class.
Bye. Have a great day, everybody.